Hello, AP Physics class. Today in Unit 8, we're exploring Day 6, which is rolling motion. If you want to follow along on the notes, starting on page 25 here, we're going to be looking at how rolling motion works and in a straight line kind of trajectory here. So kind of building on some of the stuff we learned last time about torque and applying it to a new, different system. So in a rolling system, it's a really kind of a complex motion if you think about how an object moves, right? When we were together in class, we actually talked a little bit about this, but it's a combination. So if you look at a single point of a wheel as it's moving, that creates kind of an arc, kind of a parabola motion. The center of the wheel, the center of mass, follows in a straight line, and that's what we would typically measure, right? If we're measuring velocity, we'd look at how quickly the object is moving from one place to another. But rolling is kind of complicated. It's a simple harmonic motion where that position goes up and down in a cyclic manner. So, but it is moving in a straight line. So if you traced out that one position over time, even though the object is moving with a constant velocity, the point on the circle here is going to come in contact with the ground, move up and move back down. And we talked about how at the bottom it's momentarily motionless, when it comes in contact with the ground. And that's one revolution of the wheel. So you can see it from the origin to the top, back down to the origin. And this is for a sphere that's not slipping. So it has good contact with the ground, and the wheel isn't burning out or anything like that. But our position is typically measured from the center to center, right? So, or like leading edge of the sphere to leading edge of the sphere, whatever it is. So the distance is equal to one revolution, which is 2 pi r, right? So your radius, the circumference of your circle, basically is the distance that that object rolled. That's going to be an important concept here in a couple of minutes. So, but that's basically what's happening with rolling motion is you're rolling the entire circumference of that sphere from beginning to end. All right, so how can we use that to have some meaningful, conversion, let's say? So we can measure how quickly, something is rolling down a ramp, look at, where it was before, where it is after, how long that took, and we can measure the distance of that object rolling. So how do we use that to figure out its velocity, its longitudinal velocity? Well, if we know that it's, moved one circumference, that's like your delta x. Your delta x is equal to the surface, the circumference making one complete rotation. So your delta x is really equal to 2 pi r because we're talking about the circumference of that circle for that time. Okay, so that's velocity. But we're interested in angular velocity. And if you remember from before, the angular velocity, the w, is related to the radius of that rolling object. You can convert between velocity and angular velocity just knowing the radius of that material. Okay, so, and that's the connection between those two systems. Like, if you know the distance of the rolling object, what its circumference is, then you can figure out its velocity pretty easily from that. And then you can use that to figure out the angular velocity of the rolling object. So they refer to that as the rolling constraint. which is the link between the translational systems and the rotational systems, like we're looking at here. All right, another application of the rolling motion, just to really drive it home how complicated this actually is. In terms of the angular, velocity, it's complicated because the angular velocity is experiencing both a negative and a positive effect. So here we have the translational motion, and you can see that the entire object is moving forward with the same translational velocity. Okay, so the middle is moving forward. It's as if the top is moving forward and the bottom is moving forward with the same translational velocity. With rotational velocity, though, in the rotational system, the top is moving forward at that angular speed, but the bottom is moving backwards at that same angular speed because it's spinning, right? So you have the top spinning forward and the bottom spinning backwards, essentially, counter to its forward momentum. So, well, forward motion, not momentum. So if you combine those two together, if you add the translational and the rotational, you can see these two vectors actually sum up to equal 2 times their velocity. Okay, so the top of the cylinder or sphere, whatever we're talking about here, is actually moving combined twice as fast. The middle is still moving forward at the same rate because it's not really rotating. It's staying in one position as the wheel rotates around it. That's the axis of rotation. So that's moving ahead with the normal translational velocity. But the interesting part is the forward translational velocity and the backwards rotational velocity of the bottom here equals 0 rolling speed. So that's why it's motionless. It's instantaneously at rest at the bottom of the wheel or whatever we're talking about here. So this is the idea of rolling without slipping. Like, it's not slipping. It's coming into contact and instantaneously it's at rest. There's no, sliding back and forth. It's in contact with the ground. The ground doesn't move, so therefore it's instantaneously, when it touches the ground, at rest. And that's what we mean by not slipping. It's 0, just like the ground. If it was moving, then the ground might be getting kicked up, or maybe the surface of the wheel gets rubbed off a little bit. But for all purposes, it's in contact with the ground. So therefore, it's not moving. Okay, so let's say you're going on a little trip. This has to be a trip, by the way, that's approved by the governor of the state of Maine. You can't just willy-nilly go driving around. But you're going to go for a 60-mile trip. Maybe you got to go to, Walmart and get a whole pallet load of toilet paper, right? So, and the only Walmart that actually has toilet paper is in 60 miles away. What is that? Like Waterville, Maine? So you got to go to Waterville, Maine to get a pallet load of toilet paper so you can sell on Facebook Marketplace for 1,000 times the price. Okay, this is a great pyramid scheme, to make a ton of money off of other people's suffering, which is perfect, right? So for this system, we have some big dub wheels here. Maybe you got a lift kit and a 33-inch super swamper. It's got 0.6 meter diameter. That's a diameter. Okay, so it's not that big, but that's okay. And we're going for a 60-mile trip, and we're only traveling at 45 miles an hour to not alert the authorities. Or maybe the back of your truck is full of toilet paper and you don't want to lose your precious cargo. So you're going to drive 45 miles an hour constantly no matter where you're at. It's probably an average speed, I'm guessing. So during this trip, we're going to calculate your tire's angular speed, and we also want to, for some reason, find out how many times your wheel made a revolution to make that trip successful. Okay, so here we have your tire with a diameter of 0.6 meters. We know that the trip has a length of 60 miles, and we're going to be traveling at 45 miles an hour. Now these are, standard American units, which is a problem because we don't measure in physics miles per hour. Oh, that's in meters. Excellent. So, we will have to do some conversions to get it to work. But let's first figure out our velocity in, our typical units. So we have 45 miles an hour. We do have a factor for this. There's actually 0.447 to 1 comparatively between miles per hour and meters per second. Okay, so that saves us a little bit of conversion because usually you'd have to go from miles to meters, and then you have to go from hours to minutes to seconds. So it's kind of nice to have a quick conversion where you just have to multiply by 0.447, and that's pretty much 20. So we're moving along at 20 meters per second. That's good to know, actually. If you're traveling 45 miles an hour, you can say triumphantly, hey, I'm only going 20 meters per second. So that's your speed. So let's see what we're doing as far as your, what is your angular speed going to be then? So your angular speed, if you remember from our equation before, is going to be your V over your R. Okay, so our angular velocity is a relationship between the velocity you're going and the radius of your, circle. In this case, it's your wheel. We have a diameter of 60 meters, but if you divide that by 2, then that's 60 meters, 0.6 meters. That would be a gigantic wheel. So you're looking at a radius of 30. 0.3. So let's put that in. So we have a velocity of 20, we just found, meters per second. And we have a radius of 0.3 meters. So we'll take the 20 I already have, divide that by 0.3, and we get 67. Okay, so that's 67 radians per second. Totally rad, right? Totally rad per second. Radians per second. So that's your tire's angular speed. As your tire is moving around its axis at 67 radians per second. Okay, so the translational speed was 20 meters per second, but the wheels are actually spinning at 67 radians per second. Okay, so how long does the trip take? Why do we need to know that? Oh, to figure out revolutions. Okay, I ran out of room. So your my periodic table's in the way. So one of the fundamental ideas of time is that it travels a certain distance, for that velocity. So your distance traveled over your velocity. I'm going to cheat a little bit because we actually do have the distance traveled in miles per miles. And if we use our velocity in miles per hour, miles will cancel out, and it will tell us our distance, our time in hours, which is, we can convert that pretty easily. So that's 1.33 hours, and times, so how many seconds are there in an hour? So we got 60 times 60 is 3,600. So we're gonna say 1 hour is into 3,600 seconds. So 1.33 times 3600 gives us, the trip should take around 4,800 seconds. All right, so knowing that, we can then find out the amount of radians that you would cover, because we're trying to figure out how many revolutions that is, how many turns we have of the wheel. So let's figure out how many radians total we have for that trip. So you're looking for your delta theta, which is equal to your angular velocity, your W, times the change in time, delta t. So we previously found that it was 67 radians per second. And we're going to multiply that by 4,800 seconds. And 4,800 times 67. You'll notice that seconds are going to cancel out. So we're just going to have a total amount of radians. And that's 321,600. 312,600 rad. All right, so that's not how many turns, though. To find out how many revolutions the wheel actually had, all we have to do now is divide it by 2 pi, okay? Because we want to know turns, and each turn is 2 pi, right? In the unit circle, revolution is equal to 2 pi. Half a revolution is pi. So we're going to just divide this to get it out of rads to turns, like revolutions. We're going to divide this by 2 pi. And we get around 51,000 revolutions of the wheel. Okay, 51,000 revolutions of the wheel. So in making your trip a reality to steal toilet paper, your tires are moving at 67 radians per second, and they have to rotate 51,000 times in order to successfully get back with the goods. Okay, so that's just a little bit of information about how rolling motion works, and hopefully that helps explain the notes and the concepts for you there. Thanks for tuning in.